and it started up much faster this time. That's good. So I thought it might be good to, even if people aren't doing the optional project, I thought it might be good to have a look at how you would go about doing either the VGA or the infrared controller piece, because there's a lot going on, and I think it's interesting to understand what's going on, particularly because they're, and maybe I should update my notes for HDMI, because that's the more usual video standard these days, and next time I teach this course I will certainly try and move to HDMI. The only problem I have with that is the board that we're using doesn't have an HDMI output. So anyway, VGA kind of works. I've got a VGA monitor. Till I got my new machine earlier in the year, I was still running a VGA monitor. So in fact, it's so old it doesn't even have an HDMI input. So okay, so let's we are recording, just to remind you, and it's currently streaming live on YouTube. We are nearly there. I have made available the slots for the final exam, even though I haven't yet released the final exam. I have a first draft of the final exam put together, but I need to, now that I've got a first draft, I need to go back. As per the midterm, there will be an oral component and a written component. The written component will require you have access to Quartus and potentially Simulink. Sorry, not Simulink, Model Sim. Right? So make sure that you have access to that either on the Citrix server or on your local machines. Okay. I will release that final exam next week some stage. I will send out an announcement when the paper is ready. Because the part around Quartus will be available before your time slot, that means you can actually do some preparation. However, just like, in fact, I don't think I did it for this one, but I will add a slight wrinkle to the question during your 2-hour time slot. So you won't be able to just immediately submit your prepared answer to the written components. It shouldn't be too much, right? I'm not a big fan of exams that really stretch your ability to do stuff in time. I'm not a big fan of giving you the whole semester to do the first assignment, but I think a reasonable amount of time is the right thing to do. Just from a learning perspective more than anything else. Okay, again, that's where we are. There will be no class next week, funnily enough, because the university is closed for the Thanksgiving recess. So please give thanks and have turkey. And I personally don't like turkey that much. I know that's not the right thing to say, but I love all the desserts that happen, so I'm going to be having lots of desserts next week. This is just the slide that I had last week. I did email the 3 people who did not have keys for the game. I have sent them access to the game, so I haven't heard back from them whether they were able to access it. But please take an attempt at the game. Spend some of your Thanksgiving recess playing the game. Okay, it's work, but it's kind of fun too. I think if you're in the CET program, then you probably have a little bit of interest in that sort of stuff anyway. And just a reminder, that's roughly how I'm going to determine your final grade. I will really, option A and option A plus and option C and option C plus are the same. The only difference being whether making the project optional. I will calculate all effectively 4 options: the syllabus, option A, option B and option C, and option A and option C will include a bonus for the project if it's done. So over the break you should see those 4 values, and then a maximum of those 4 values appear in Blackboard, so you'll know where your grade for the semester is heading. Note that that won't be your final grade for the semester, because there's still outstanding labs and outstanding the final outstanding, so that can increase or decrease your final grade, your overall grade. I try and avoid using the word final grade because that sounds like it's the grade for the final exam. So the overall grade.
Professor, could you double check if you're streaming on Discord? I don't see anything up.
Oh, you don't? Okay. Maybe I'm not. That's probably right. Oh, yeah, I don't think I did. Sorry. Where's Discord gone? There's Discord. You're right, I did not. Sorry about that. And let's go with screens, and let's go with screen 2. Okay, sorry about that. Yes, that should make life a little more seeable. And okay, sorry, I didn't see the I didn't see the chat. I should have had the discussion up, and I might have seen it. Sorry about that. Okay.
All good.
Yeah, I haven't had enough coffee yet this morning. Yeah, so those are the options for how to determine the grade. I sent an email this morning to the people who have yet to do Lab 6, and I also noticed that so far only one group has managed to complete Lab 7. So please get Lab 6 done and get Lab 7 done. Thankfully it looks like everybody's done Lab 5, so we should be good to go. And does anybody have any questions about the grades, or how I'm going to determine them, or what we need to do to get to the end of semester? No? Okay, so let's move on. And I thought I needed to refresh my memory about how this project worked. This is it's like a Pong game project, and I thought it would be also good if I can figure out where it got to. No, I don't have it open, so let's see if I can open it up. It's in 466 and 2018. No. Oh no, it would be in this year's, I think. Oh no, it's in the GitHub repository, sorry. So what I probably should do, although maybe that's not the most sensible. I was going to say I should put all of my CET466 stuff in the one repository, but I don't want to give you access to my exams before they're ready anyway. Examples. There we go. So I thought this might be worthwhile having a look at, right, before we go in. This is the board we have being connected to a VGA monitor, and I'm pressing the buttons, and you can see because the VGA output that we have is only 1-bit resolution, and there's 3 colors, red, green and blue. I can only get a total of 8 different colors, and you should be able to see the 8 different colors on the screen now, right? So there's black, red, yellow, green, white, cyan, magenta and blue. Right, so there's those different colors, and I thought it might be good to have a look at how the board is producing those colors, right? And the example Verilog code that came with the board generated this VHDL. Sorry, this VGA output. Okay, so there's that. So that's kind of fun, I think. So let's have a look at it. So the VGA connector is one of those, and let me just see if I can show you. Where's Streamlabs gone? And let me go to the bigger me version, right? So that's the sort of connector it is, right? You should have seen one of those. It's a bit hard to see there. The lighting's not the best on the end there, but there are 3 rows of pins inside that shell, and that's what the VGA connector looks like. And these are the connections on the shell, right? On the pins for the VGA connector. There's 1, 2, and 3, which is red, green, and blue, which is I've put in colours there. There's a reserved, ground, red return, green return, blue return, plus 5 volts, ground, reserved, I2C data, horizontal sync, vertical sync, and I2C clock. The only thing we need to do, or the only ones we need to make, where's my pen gone? And let's see if we can get the draw menu up. The only ones we need to do are, or to use, are red, green, blue, and their associated returns. Horizontal sync and vertical sync. In fact, the only thing we need to actually generate in order to make a video signal are the circled ones: red, green, blue, horizontal sync and vertical sync. In order to make the connection, we need the red return, green return and blue return, as well as ground. Some devices do some extra levels of control using an I2C bus, right? I don't know whether my monitor uses those at all. I haven't checked, and I don't know whether there's a standard for what goes onto that I2C bus. There may very well be a standard, but I'm not sure what that is. Okay, so what we've got to do is for our Vhdl code is generate all of those signals. Okay, so that may be a little. And what does that generate all of those signals mean? Well, if we have a standard VGA screen, which sounds incredibly low resolution these days, 640 pixels by 480 pixels, then each one of those little pixels, that little tiny red square up in the top right corner, right, this one here, that's, let me just put my VGA cable back so I don't keep bashing into it. What we've got to do is when the that particular pixel needs to be set, we need to have the appropriate red, green and blue bit set to make sure we get the right color here, that we get a green color or a red color or a blue color or a magenta color or black and white, yellow or cyan. Okay, so how do we do that? Well, what's happening is we've got to have two syncing signals, synchronization signals, and they're the horizontal sync and the vertical sync, right? Pins 13 and 14. So what happens is the horizontal sync, that's the black line there, tells you when you're supposed to be at a particular pixel, right? And you have to hold your red, I probably should draw that in black, but anyway, you've got to hold your red, your green and your blue signals at whatever value you want them to be during that interval to identify that particular pixel. And so what we're doing is we're going across this screen. Let's just get a black color up. We're going across this screen and we're saying, okay, there's that pixel that's got that color, here's the next pixel, here's the next pixel, here's the next pixel, and we're going all the way across to here, and then we're saying, okay, now we need to move down, right? And then we do this pixel. So this is the horizontal clock or sync, and then this piece is the vertical sync. Okay, and that's what the next line down is doing, right? Here we've got a similar clock signal, but now we're telling the device to move down a row of pixels. And all this is showing is we've still got the red, green and blue signals happening because they've got to keep going, and all this is happening. This piece here is just showing that this top diagram is just a really zoomed in version of what's happening here. Okay, and this particular piece here is us going down the rows of pixels. And here's some example numbers, right? So we've got in our colored signals, we've got to keep some space on either side of the horizontal sync, and that space is called, in one case, the front porch, and in the other case, the back porch. Right? It's a cleared area around the synchronization clock. And in fact, let me go here. This might be better to start with. Right? And this is, if you like, what is happening in reality as far as the different porches and pixels is concerned. If you want your visible screen to be 640 pixels by 480 pixels, 640 pixels wide by 480 tall, then effectively, because of the requirements of the front and back porch on both horizontal and vertical syncs, you need to have an effective window of 800 pixels by 525 pixels with those numbers selected. Right, and those numbers, and I took those numbers from this tinyvga.com website, so have a look at that. And in fact, I did access it this morning, so it is still there. And these are two examples of possible Vga timings. The one I put on the next slide is the general Vga timing, right? It's this one. And then there's so this one, the refresh rate is 60 Hertz, and the vertical refresh, that means, is 31 kilohertz, and the pixel frequency is 25.175 megahertz. And then we get all of the numbers in terms of both pixels and time based on those frequencies, right? So 640 pixels is going to be 640 times the period of 25.175 175 megahertz, which gives us 25.4 microseconds. And then we've got the front porch number in pixels, the sync pulse number in pixels, the back porch in pixels, and the whole line in pixels. And then similar numbers for the vertical timing. And then on the right hand side, it's got a slightly different setup. This one is an SVGA, which is I think I've forgotten. I think it's Super VGA, but anyway, it's the slightly higher resolution, even though it's laughably low by today's monitor standards. And this one is an 800 pixel by 600 pixel viewable area. The refresh rate is 56 Hertz, and that means that the whole line width is 1024 pixels instead of 800, and the whole frame timing is 625 pixels rather than 525 from the standard VGA. Okay. Any comments or questions about that? So I thought it might be good to also have a look at code.
I have a quick question.
Yeah, what's up, Harvey? What do you got?
Are you able to force the VGA to scale up higher? Because for some reason, I have a memory of it. I had a memory of it going up to like 720.
Oh, yeah, of course. These are just two examples, right? So this is from that tinyvga.com, and you know it'll go up, or rather it can get up to something more sensible, right?
But I see that clock speed.
Right, but yes, the clock speed is just way too fast for our board, right? The pixel frequency is 234 megahertz.
Okay. I
Okay.
see what you're saying.
Right, so, you know, for our board, we've got to choose something achievable, which means the pixel clock rate has to be, so maybe we could get it, but again, it looks like that's a slightly different standard. That's a VESA standard rather than a VGA or SVGA, but I think it uses the same. That one may be achievable, right? 44.9 megahertz, and that's 1024 by 768. Okay.
Oh, thank you.
You're welcome. So, you know, look at this one down here. It's 1920 by 1440, which is a more closer to what a lot of screens are now. And it's also a much faster refresh rate at 75 Hertz. But look at that pixel frequency, right? 297 megahertz. That's not outrageous if you compare it to a CPU clock rate, right, which is of the order of gigahertz. But compared with our board, with a tiny 50 megahertz clock rate, it's a little out there. Okay, and I'll put this link into the links channel in wherever it got to. Links, there we go. Okay, so that should be there now. Okay. So I thought it might be good to have a quick peek at now that's the wrong one, is it? Yes, they're the wrong ones. That's the one. So this is for a different board, but we got it to run on the old 466 board. And I will make this code available in the GitHub repository, so you can access it if you want to have a look at it. Right, so this is one of the entities, Vga drive, and let's just read what it's doing. It's taking in a clock, and it's got to be in this case it's got to be a 25.175 megahertz clock. Right, let's just go back to our did I see that there somewhere? Right, so that looks like it's this 25.175 640 by 480, and look at the numbers 16, 96, 48. And let's go back to Visual Studio Code. Right, so we've got an input clock. Of that we have red, green and blue inputs, and output we have a row and column for the current pixel, and we've got the red out, green out, blue out, horizontal and vertical out as just single logic signals. Right, so those are the things that drive the monitor, and the row and column outputs are used to know when to assert red, green and blue for the current pixel. For VGA, the column values are, in this case for the resolution we're using, is 0 to 639, and all other values should be ignored, and the row values, again because of the resolution we're using, are 0 to 479. To turn on a pixel, you need some values on those red, green and blue, and they should be asserted before the rising edge of the clock. Objects that are displayed on the monitor have their red, green and blue values basically put on the screen. Right, and if you want to have multiple objects on the screen, you've got to combine the information about where you are on the screen with the red, green and blue information in order to say, yes, I want to turn that pixel on. If it's a ball and it's white, then I need red, green and blue to be 111. But if it's a paddle and it's red, then I need its pixel values to be 100, red, green, blue. Okay, and here are some of the constants. This is the entity, or the port statement, right? And here's the architecture for that port. And they've got decided to have a counter, and we've got the horizontal blank interval is set at 93 pixels. The front guard is set at 45. Front guard or front porch, right? There's the number of columns. There's the back porch or rear guard, and there's how long our full horizontal line of pixels is, including all the stuff that's happening off screen. And then we've got the same thing for the vertical blanking interval and the front and back porch, and then again the vertical sync interval. It's going to be P, Q, R, and S. Okay, and then we've got some stuff happening. Remember, we're taking red, green, and blue values in, and in our inside our architecture, we're just wiring those red, green, and blue values straight to the output. Right? We're not doing anything by the looks of things. We're not doing anything to change those input values. We're just shoving them straight out as soon as we get them. Okay, and then I wish this, oh, maybe it does. Right, there's a single process inside this architecture. Right, and let's have a look at what's happening in the process. We've got some counters, and we defined the counter type up here to be a 10-bit value. Right, 10-bit values are going to be able to count from 0 to 1023. So that's probably okay, since we only need to get up to, what was it, 800 is the biggest number we need to keep track of. So that's probably okay. So now let's have a look at what's happening inside. And we wait until the clock is equal 1. So we wait until we get a nice positive clock, and then we increment our counters if our horizontal value is less than a minus 1. Right, remember a was how long our horizontal sync was in pixels. Then we just increment the value of horizontal. And otherwise, if horizontal is A or bigger, then we reset horizontal to be 0. This is just because, remember, horizontal is of type counter, which is a static logic vector. This is just a shorthand way of setting that static logic vector to all zeros. Okay, the other thing to notice is these counters are all variables, right? So the assignment for the variable is a different assignment compared with signals. Remember, the signal assignment is less than equals rather than colon equals. Okay, so that's what the horizontal sync is doing. And remember, once we've gone through a whole line of horizontal pixels, we need to change the vertical pixel number, right? So we do something very similar. Remember, O was our duration of the vertical axis in terms of pixels. So if we're less than O minus 1, we just increment the vertical counter, and otherwise we set the vertical counter to 0. Okay, so you've got those two things happening. You're with the value in horizontal and vertical, you can tell exactly which pixel we're going to be on, right? So let's go back to the right. So here's our horizontal. And right, we get a particular value, and here's our vertical, and we get another value, and that says, okay, I'm dealing with this pixel right now. Okay, that's part of it. Now let's figure out how to do the pulses. Right, and the horizontal pulse, if the counter for horizontal is greater than d plus e and less than, greater than or equal to d plus e and less than d plus e plus b, then we set, now remember h is a signal, so we use the less than equals assignment operator. We set that to 0, otherwise it's 1. So let's go back to the, where's it gone? That one. Right? So this is the horizontal signal. Right? So we're looking at what's happening here. And let's go back to D, E, and B and figure out what's happening there. There we go. So we got D and E, and D, E, and B. What's D and E? D is the length of our viewable area, the width of our viewable area. E is the rear guard, and B is the horizontal blanking interval. Okay, so this is the horizontal blanking interval. And where's it gone? There it is. Okay, so that generates the H output. Notice this process that we're looking through at the moment has nothing in the sensitivity list, right? So it's going to just keep firing, and the only thing that's going to reduce how often it fires is that wait at the start of the process. Remember, the difference between these things here outside the process statement and anything inside the process statement is that these three things happen all at the same time. They're just a wiring up of the inputs to the outputs in this case, whereas the process statement happens sequentially. And in this case, there's going to be a wait happening until we get a positive going clock, or at least a positive clock. And then similarly, the vertical pulse is set up according to R and S and RS and P. And remember, we have a vertical blanking interval, which is going to be part of figuring out how that works. Okay, and then once we've figured out the vertical and horizontal counters, we've figured out the horizontal output and the vertical output, we can say, okay, the output row comes from the vertical counter and the output column comes from the horizontal counter. Okay, so that allows us to take, what's it doing, right? It's allowing us to just take a clock in and the value, the red, green and blue values we need right now, and output a VGA signal. So the question is, how do we use it, right? How do we make sure that this is all happening appropriately? Anybody got any questions about this particular piece of code? One thing I would note, right, is we've got, this isn't new stuff. This is, that's partly why the VGA thing is a little old anyway. This is coming from quite a while ago. So the other piece is it makes use of this VGA driver. This thing's called Vga drive, right? The other piece is a way to test it, right? And again, this is coming from quite a while ago, and it's just the aim, I think, initially was to just generate a Vga test pattern, but I think this has actually been updated to do something else. Let's see if we can figure out what it's doing. Right, so Vga test, and what have we got? We've got a clock coming in. That sort of makes sense. We've got an X button and a Y button. We've got a red switch, a green switch and a blue switch. We've got a size switch and we've got a direction switch. So they're all our inputs, and for us, I think 1, 2, 3, 4, 5, 6, 7. We only have 4 buttons, so we probably wouldn't be able to do this one. And here's the outputs: red, green, blue, horizontal and vertical. Remember, this is going to, well, the aim is to connect this up to the output. So here's our architecture, and here's a component. This is a component of the thing we just looked at, right? And then we've got some signals in our architecture, a row and the column, and the red, green and blue values. Here is an instantiation of our it's interesting. Why does that one help and that one not? Anyway, here's an instantiation of our Vga drive component, and it maps all the appropriate things, right? Our R out is going to our R value, right, etc. And then we have right, then we have a process statement, and the process statement has a sensitivity list if the row or the column changes and it's going to do something, and then if any of the switches do anything, it's going to do something. And it's got some variables inside the process statement. Remember, we've got signals for the architecture, and we've got variables inside the process. Signals are values that will live outside the process statement. Variables are values that do not live outside the process statement. they're only intermediate values. Okay, excuse me. Here is the first thing, right? If we have a value of switch size is 1, then that's changing the size of the block. It looks like we're putting a block on the screen, and in one case it's going to be 20 pixels across, and in the other case it's going to be 40 pixels across. Right, and then we've got a rising edge statement on the Y button, and if the direction in the Y button, if the direction switch is 0, then we increase the Y position by 40. If the direction switch is 1, we decrease the Y position by 40. Similarly for the X button, we have a direction for X, and we either increase the X position or we reduce the X position. And we want to make sure that we keep the position of the box on screen. So here is just a check if Y position is greater than the size of the screen. Then we set Y position back to 0. And similarly on the X axis. And then we also want to check going the other way, because we don't want to go to negative 40 pixels or negative 20 pixels in either X or Y. So we set it to going back. Any questions about what's happening in this code so far? Okay. So then we have actually doing something with the red, green, and blue values. If our row, our current row, is where the Y position is, and within those values of within block size of the Y position, and if our X position is within block size of the X position, if our column is within block size of the X position, then we'll use whatever color is being set on the switches. Otherwise we'll set black. Okay, so what this should be doing is it's just letting you, it's going to put a block on the screen. You can change the size of the block between 40 pixels across and 20 pixels across. And you can move the position of the block. And that's about it. It starts the block in the center of the screen. If our screen is 640 by 480, then 240 by 320 is roughly in the middle of the screen. Any questions about that VGA wise? No? Okay. Like I said, I will make that code available in the what do you call it, GitHub repository, but I suspect that code is already available. Right, so there's our there are our two. I'll put that link so you can see the And where are we? Links. Of course, we need to connect everything up appropriately, right? So we need to look up our pins, and here are the VGA connections that we need. A horizontal sync is pin 101, vertical sync is 103, red is 106, green is 105, and blue is 104. Okay. So let's go back here. Right, so that's an example of how you could think about VGA, right? I know that actually that's a good point. Let's see if we can find. There is in the where's it gone? There. There is in there it is. In the repository, this file, which is vga.v, note that that is a Verilog file. It's not a VHDL file, so it will look a little different. But you should pretty much be able to see some of the same things, right? Here is a definition of the horizontal sync end, and it's 95 pixels. Here's the data end, it's 143 pixels. Begin is 143, here's the end, 783. Right, this is a slightly bizarre way of saying it's a base 10 number. We've got a clock that's just dividing the incoming clock by a factor of 2. This is like a process statement, right? And it's taking that VGA clock and deciding whether or not to either just increment the horizontal counter or set the horizontal counter to 0. Here's another effectively process statement, and this one is doing the vertical counter. Right. And here it's outputting the, depending on what the switches are, it's putting something out onto the data line. And depending on what is happening with the vertical counter, it's putting something different out on H data, and here this one's depending on what the horizontal counter is doing, it's putting something different out on V data. Okay, what this VHDL is doing, sorry, what this Verilog is doing is, oh, where'd it go? Is precisely this, right? So it's either putting vertical stripes or it's putting a logical relationship between the vertical and horizontal values. Let's go back and see if we can figure that out. And that is being done here. Right, if there's the switches, the two switches we're using both 0, then we output just the horizontal data. If one of them is 1 and the other one's 0, then we output the vertical data. Otherwise, I think that is exclusive OR. I think. I've forgotten what that is in VHDL. Sorry, in Verilog. Let's see if I can find it quickly. Yeah, it is. It's the exclusive OR. Sorry, I haven't done Verilog in a very long time. So, where's our... Right, so that is doing the exclusive OR between the horizontal data and the vertical data. And it's doing the exclusive NOR, right? That's what the tilde is usually a complement or a NOT operation. But those two together make it exclusive NOR rather than exclusive OR. And that's why the pattern changes, right? In that video, right? It changes from that to that. Right? One of them's the exclusive OR pattern, and the other one's the exclusive NOR pattern. Just the vertical lines are the default, and then it does the one or the other depending on exclusive OR or exclusive NOR of the values, depending on which button you're pressing. Okay, any questions so far? So I haven't prepared as well as I'd like for this next bit, but I thought it might also be instructive to have a look at the infrared stuff. And let me just see what we've got. Right, so what happens with the infrared detector is it's a sequence of pulses that where is it gone? That the remote control device generates, right? That thing. Let's where's it gone? There we go. Right, so that remote control device has a, you can't really see it, there's a little infrared LED just there, and that generates a sequence of pulses depending on which of the buttons you press on the remote control. And this is an example of those pulses. And the thing is, this sequence of pulses is a communication protocol, right? We're not the nice thing about the VGA is everything's in lockstep, right? We know that we need this pixel, this pixel, this pixel, this pixel, and that's the only thing we need to change is the red, green, and blue values depending on what we want to display. So the difference with the infrared is now we don't know when somebody's going to press that button, right? So we've got a and the actually I won't. I'll probably upset too much if I show you the infrared receiver on the board. In fact, I can probably show it to you here. Right, so where has it gone? I think it's this device here. Yeah, it's this one here. That little silver thing right beside the 4 switches, that's the infrared receiver there. Okay, and so because you don't know when the person is going to press that button, right, it's not as synchronized as the VGA. You've got to do some what's the word? You've got to do some checking on the signal, right? You have to keep checking the signal, and there's got to be a protocol that says, hey, I'm sending you something, and then there's a piece that says, here's what I sent you. All right, so the first bit is the problem is synchronization, right? We have complete control in the VGA case of synchronization of clocks. We can set rising edges or falling edges or values of the clock or wait untils of the value of the clock, right? That all works nicely. I don't have any clock connection from my thumb to the board, right? So there's no way I can easily synchronize my actions with what's happening on the board. So that's why you need the protocol. And unfortunately, I only have the code that came with the board, and that's in Verilog rather than VHDL. So I probably should look at translating it. But let's see if we can make some sense of it. Right, and what this one's doing is it's pulling in data into the get data signal. Reg is like a signal in. So here are our inputs, and what this one is doing is it's taking in the clock in a reset value and the level from the infrared detector, right? And then what it's outputting is the chip select on the particular 7-segment display and the value to show on which of the 7-segment displays it's being shown. Okay, so I haven't actually run this on the board. I might see about doing that this morning once I finish talking, which should be reasonably soon. And it'll show you what's on the board. So let's have a look. Right, so there's lots of stuff happening here. Right, and part of it is to do with the protocol, and part of it is to do with sending the data to the 7-segment display. And I'll start here, right? So sorry, I'll start here. Always in Verilog is like the process statement, and then we have a case, right? And that's like a switch statement or a select statement, right? So here we've got let's see if we can figure out where the states are defined. I think it's up here somewhere. Maybe not. Where's it defined? There we go. Right, so we've got we're using these values the way you would say this in VHDL, is using the either the generic or the constant statement, right? So we've got idle, leader 9, leader 4, or data state. Right? Idle is when we're not doing any processing and we're just waiting for something to happen. Okay, so, and then the data state is when we're processing the data, and then the leaders are two things where we're waiting for something to happen. Right, so here's our idle, and if we get something happening on the infrared input, then we go into the leader 9. So that means that there's a 9 millisecond lead-in time that we have to wait. Once we get into that state, so if that happens, then we're good to go. If it doesn't happen, then we just stay in the idle state and we keep waiting for something to happen. Then we swap over into the leader 9 state, and if we get a negative pulse, then we can check to see whether we got an appropriate time into the leader 9 state. If we got in an appropriate time, and it looks like it's 9 milliseconds, if we got an appropriate time into that leader 9 state, then we can go to the next state, which is leader 4. If we didn't, then we go back to idle, because it was just noise that came in. Maybe there was somebody lit a match, and it looked like it was going to be an infrared signal coming in, but it wasn't. So we just stop. If there's no pulse, then we just stay in this state, and we're good to go. Or at least we're still checking our 9 millisecond. Let's just see if we can find where that check 9 millisecond happens. Right, so here's our check 9 milliseconds, and it's saying that and in this case this is Verilog. This is Verilog. So the ampersand is actually a logical AND rather than concatenation like it is in  So this is saying if our counter is greater than 217 and less than 297, then our check 9 milliseconds is good. And otherwise, otherwise check 9 milliseconds is not going to be useful. Right, and then leader 4 is something very similar, and now we need a negative pulse, excuse me, instead of a positive pulse. Right, this one was a positive pulse, this is a negative pulse. We do something very similar for the 4.5 milliseconds. Right, there's our again, we're going with our counter 2. It has to be between 88 and 168 counter 2 in order for check 4 milliseconds to be true. And if our check 4 milliseconds is true, then we can go to the data state. And we stay in the data state if none of these, if there's no error and if that condition is not true. If there is an error or if that condition is true, we jump all the way back to the idle state. And if we don't know anything else, then we just go back to idle. Right, and here's the processing for the idle state, for the data state. And we check, and if we have an error, we flag that. Otherwise, if we've got a low value, we put that into the data. Otherwise, we've got a high value, we put that into the data. Otherwise, we throw an error. Okay, but the key thing I want you to get out of this, okay, I'm probably confusing the issue because it's Verilog rather than VHDL. The key thing I want you to get out of it is this state machine, right? We start off in an idle state, we get something that we think might be a signal coming in, we check that that's still coming in for 9 milliseconds. Then we move to the next state. Okay, it was coming in for 9 milliseconds. Let's go to the next check state, which is the leader 4 or 4.5 milliseconds. We're good there. Okay, now we know we've got something that we need to read, and then we start reading that data. Okay, that's, I think, where have we got to? That's, I think, about all I had for this morning. The previous time I taught this, we spent a lot more time during class in the labs because we're in person. I've spent quite a bit more time talking about stuff in this semester. So what I'm going to do is I'm going to take I'm going to get some questions shortly, but I'll take a 10-minute break, and then I'll try and get that infrared Verilog version demo working, and I'll try and show you how that works after the break. But before break, does anybody have any questions about what I've just talked about? The either the VGA stuff or the little bit I talked about with the infrared. Okay, that sounds very quiet. Never quite sure whether quiet is good or bad. So let's go with our usual 10-minute timer. I'm going to, the rest of this morning's session, I'm happy to work with labs. Please check your email. If you haven't done Lab 6, let's get Lab 6 done today. and that way when we return we can just focus on getting labs 7 and 8 done in your groups. But let's take that 10-minute break first. Okay. We should try the electric. What's the electric 10-minute clock? What am I missing, Anthony? This one here? Oh, I see what you're saying. Yeah, this. Yeah, that's kind of cool. I don't know whether I can stand the music though, so I might have to turn that down. Okay. Okay, so where are we? Where's that gone? There we go. So, like I said in the email that I sent several of you, you need to get your Lab 6 done. I've only seen one submission on Lab 7, and I know that group has also pretty close to finishing Lab 8. The reason I know they're pretty close to finishing Lab 8 is because I stole their code and did my little example of the baseball. So let me try and do this. I was going to try. Where's it gone? There it is. I don't have anything. Okay, thanks, Anthony. That's good to know. I'm going to try and have a look. I've opened up that infrared example code, and the problem I have is that I can't, when I try and program it, it's given me the wrong device. And when I auto detect, it comes back here and gives me that one. I think it was EP4C6. Maybe CE6, but I just want to check that that's the right one. So I'm just going to go back to my other project, and let's go with that one. That should be enough, I think. And I just want to check to see what the program device options there are. So there it is, EP4CE6, so that should have been right. Let's just check to see what it says here, EP4CE6E22. Let's just take a screenshot of that so we know what that looks like. EP4CE22. E6, E22. And let's close that project and open up that infrared one again. So part of the reason I decided not to go to the Verilog using in this class is because all of these example code pieces are in Verilog, and that's a little bit too much of a crutch for me and probably for you too. So I decided to go with that. EP4, let's just check that we've got the right device. EP4 CE6 E22 C8, I think that's right. EP4 CE6 doesn't have anything else, and it's still not letting me. Ooh, for some reason it's not generating a file. Let's just go back to the other one. I'm wondering why it's not generating the file. I think it's, yeah, see, it's not generating the EDA netlist writer. So when I come here, it's got an SOF file. So I'm wondering why the project is not generating the EDA netlist writer. If anybody has any lab questions, feel free to, I'm hoping the bot is there. Feel free to join the queue. If you don't have any lab questions and you don't want to watch me try and debug this infrared thing, you're free to go off and do your own thing. You need to do an exclamation mark join queue, Yasmin, to join the queue. There we go. Okay, so Yasmin, let me talk to you.
So my question is, how should I test the Lab 8 in the test bench? Because in Blackboard it says to have detailed test bench for the lab.
Right, so what do you need to test? Right, what is Lab 8 doing? Lab 8 is doing a baseball counter. So I think this one is let's just have a little think about Lab 8, right? So let's not do that. Let's do that instead. No, we didn't want to do that. Sorry. Let's do that one instead. Right, so where's Lab 8? And we've got inferred lectures, that's okay. I didn't want to do that. I wanted to do that. I didn't want to do that. Sorry, I'm just... So what are the things we've got to test? Well,
the problem that I'm having with it is, like, in my my code runs on everything that changes runs on the clock, which is 1,000 hertz. So that means, like, I'd have to have 1,000 on 0 to 1 transitions on my clock, and I'd have to check to see that each of the conditions are met at that time. So that's what I'm having problem with. Figuring out what condition I need after that many clocks.
Okay. So the two key pieces, I think that we need to check the ball counter and the strike counter, right? So, and I'm this isn't answering the detail of your question that you just asked, because I'm not quite sure I get the, but let me play back, at least let you know what I think needs to be tested, and see if I can make if I can put your question into context, right? So the idea is that you have the ball switch, right, SWB, and it gives a single pulse, and from start that means the counter goes to 1. If we have a 2 pulses, that means the counter goes to 2. If we have 3 pulses, that means the counter goes to 3. And if we have 4 pulses, that means, well, the counter goes 1, 2, 3, back to 0, right? And the same here. This goes from 1 to 2, from 1 to 2 to 3. So I think that is easy enough to check. And now let me just try and understand the detail of what you just said. Right, I think what you're saying is this happens over 1,000 clock cycles, is that right? Yasmin, well, can you? That is right, right. So, okay. So what I'd suggest is what you need to do, right, is to make the simulation clock toggle. Right, and you need to make it toggle instead of, you know, and then wait for whatever you decide. I don't know, 10 nanoseconds or whatever it is, 100 nanoseconds. Right, instead of just cutting and pasting those 2 lines of code 1,000 times, what you can probably do is create a function that is a for loop, which goes from 1 to 1,000, right? And then just put those 2 lines inside the for loop. And this is, you know, the function's called, I don't know, 1,000 clocks.
Do I need to test the LEDs as well?
Well, that's effectively what you're doing here, right? You're not testing the value of the count.
I mean the flashing LEDs for when it resets.
Oh, okay. No, I think that might be a bridge too far. The main thing I want you to test are the correct display of the ball counter and the strike counter, and the correct resetting of both of them on the appropriate inputs. Okay? Does that make sense?
My output is the 7 segments, so what I should be checking is the 7 segments, correct?
That's correct. So yeah, you've got to you've got to check that right at the start, before anything happens, that you've got, you know, your 0 display, and that'll be a particular value of your 7-segment output. And then when you get the first ball, you need to check that you've got the ball LED 7-segment LED display selected, and that it's got the 2 segments lit up. And then when it's 2, you've got the 5 segments lit up, and same with the 3, you've got the 5 different segments lit up. Okay. And let's just have a quick look at Vhdl functions, if I can find the
So another thing, the conditions that I should be checking is that the ball increases from 1 2 3 0, and that the strike counter after that do the strike counters 1 2
right.
0, and then do ball counter and strike counter. So like check the reset of them if they reset when strike counter gets to 0, if it resets.
That's correct. So set the ball counter to 1, say, and then make sure that the strike counter goes through and resets, and check that the ball counter has also reset when the strike counter resets, and vice versa for the ball counter. You know, going when the ball counter resets, check that the strike counter has also reset.
And also the new baller.
And also the new batter switch as well.
Batter.
Okay. So I'm just going to have a quick look, and that is interesting. The notes I have don't explicitly talk about functions. Okay, so Kyle is up next. Let me nope, I need to do that version. Kyle, what you got?
So it's not about the lab so much as the game key thing.
Okay, yep.
So I figured I'd do it over Thanksgiving break, right?
Yep.
And I got my Steam account linked up with the thing, but in order to do it, in order to get it, it wants it to verify it with your email.
Oh, with my email. Ah.
Yeah.
Okay, so what do you need to do? Do you need to send me an email and I need to tell you something?
Well, I'm sending you an email, and I guess it just says check email to continue, so it's just a confirmation email, but that's...
Okay, in order to access your Steam key, click the link below to verify your purchase. I'm going to verify my purchase. That's odd.
Yeah, I don't know.
And now it's given me the... Oh, why is it giving me this? It should give you this. I specifically...
If you have a key, if you have like the actual key for it, I could probably put it into my Steam account.
Yeah, let me... I'm going to click the Get Steam Key, and there it is there, and I'm going to private actually what I'll do is inside Blackboard, if I can figure out how to get there. Inside Blackboard there should be a game key link, or a section. We'll just call key section. Where are we? There we go. And there's you. And I said it. It was set to sent email, but I've just changed it over to the game key that it just told me. And I'll send you the same thing in direct message in wherever Kyle's got to. There you are. So that should have sent you the key in.
I see it.
Yeah.
Awesome. Thank you.
You're welcome.
That was all I had.
Okay, that's all right. So I'll go back. I'm a little worried that there's no information about functions. So I'm just going to find some information about Vhdl functions and see what we've got. And maybe it should be a procedure rather than a function. Because we don't need, if for what I was talking about with Yasmin, the all we need is something like this. So let me see if I can do it. It would be, in fact, let me type it in here if I can figure out how to type here. Right, it'd be something like procedure 1,000 clicks is, and then I don't think I need anything. I don't need any variables or other stuff, so I can just begin, and then I can say, now I've forgotten the precise syntax for the Vhdl for loop. So I'm just going to go for counter in 0 to let's go 999 loop, and then I'd want to say clock is not clock, and wait for 100 nanoseconds, and then end loop. I think that's what I want to do, and then end procedure. So something like that is probably what you want to do for a procedure, right? I don't need any parameters passed into this procedure because I just want to make it easy for me to let's make it clocks rather than clicks. I just want to make it happen 1,000 times, and yeah, that should work. Okay. So I think that pretty much works. If there's nothing else, let me go back to there. Nobody else has joined the queue, so I'm going to go back to looking at that, why that IR thing is not working. Right, I've got the right thing there selected, but I'm still not getting I should, and this one is Verilog. Let's see if that helps things at all by having, we shouldn't need a simulation to generate the SOF file, but let's just see if that changes that EDA netlist writer output on the IR sample code. There we go. Now it's actually generated, done something in the netlist writer. I don't know whether that's needed. Let's have a look at the pin planner. That's the right device. All the pins look like they're set up appropriately. Clock's coming in on the right pin. So let's open the device programmer again. And it's still not generating an SOF file. Let me just see if I can do some Googling to find out why Quartus won't generate an SOF file. Ooh. Look at that. There's lots of questions about asking why Quartus doesn't generate an SOF file. Okay, so the first suggestion is to go to Assignments, Settings, and then Compilation Process Settings, and run assembler using compilation. Run assembler using compilation is set. Okay, sometimes it's saying that there's a sometimes it's saying that I have to it gets problems because the dB and incremental dB directories get out of whack. So I'm going to move them to downloads and then reopen the project and see if deleting those files does the appropriate thing. I suspect that didn't change anything. Let's check. No, there's still no. SOF file. There's an SOF file. Maybe I just had to add it manually. I don't remember having to do that before. Okay, that's interesting. Let's see if I can figure out how to pull the okay, I did that. Ooh, look at that. Okay, so let's where's my little camera gone? There we go. No, it doesn't like doing that. It needs to. Right, so this is it's pointed at something more sensible. And let's just, before we do that, let's just reprogram it. Start it from scratch. Right, so there's the board, and it's displaying all FFs. And if I press 0, it makes all the LEDs go to all 1s. If I press 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? So that's doing, it's certainly reading the numbers. It's not reading any of the others. If I press any of the other buttons, it just goes to FFs, which I think is an error condition. Right? But it's certainly reading the numbers of the remote control. And you can have a look at my peace lilies for a change. Okay, I'm assuming nobody else is interested. Abraham, do you have any questions? Quinton, Yasmin? If not, I'm going to shut down the session.
I guess I had a question about for Lab 8.
Okay, what about Lab 8?
For yours, you had a VHDL called a debound switch. Is that when is that like a VHDL to find out which, like if you're pressing a button to activate like increment for the ball count or increment for a strike count?
Yes, so what you'll find if you don't debounce the switches, it'll be very difficult to just get a single increment on the ball counter or a single increment on the strike counter. In fact, I found that sometimes it'd generate 3 or 4 or 5 pulses every time I press the button. So it'd go through and count. The strike counter would count 0, 1, 2, reset 0, 1, right? For one press of the button. So I suspect you'll see the same thing if you don't use some sort of a debounce switch or debounce code.
Okay. I'll look into that a little more.
Yep.
Thanks.
No worries. Okay, I'm going to shut down the stream to